Okay. Looking at force vibrations. First, unforced vibration, mass times acceleration is equal to negative ky, which means my double prime plus ky equals 0, giving us complex solutions e to the square root of k over mit and e to the negative square root of k over mit. Now, the general solution then is b e to the omega it plus c e to the negative omega it, where omega is the square root of k over m. And we should be totally familiar with that, but this is just kind of a quick synopsis. Well, then that can be expanded like so, using the Euler identity in the obvious way. And then we collect terms and we get this. So we have some multiple of cosine omega t plus I times some other multiple of the sine omega t. B plus c and b minus c could be set equal to any two constants, okay? Because b and c are arbitrary complex constants, b plus c and b minus c are arbitrary complex numbers. In other words, if we set this equal to c1 and this equal to c2, we can find the b and c that make that happen. So we might as well call this c1 cosine omega t plus I times c2 sine omega t. Now, of course, c1 and c2 are complex constants, complex numbers. So we do a little arithmetic and end up with the conclusion that our general solution for real numbers a, omega, and phi would be this, okay? In other words, our general real valued solution could be put in this form. There are other forms. Have to do a little bit of trigonometry to get here, but I believe I've talked about that previously. Okay, so you need to be able to fill in those details. Forced oscillation then, you add a force F of t to the restoring force negative kx, and your net force, mass times acceleration, is F of t minus kx, goes into this form, and we can solve this, if possible, finding a solution to the homogeneous equation using undetermined coefficients of variation of parameters to hopefully find integrals that give us a function for the driving function, F of t. Okay, so example, half kilogram mass on a spring with force constant 50 newtons per meter. If there's no forcing, then you just have net force is negative kx, and that leads you directly to the equation mx double prime plus kx equals 0, with m equal to 0.5 kilograms, k 50 kilograms. You plug those in and do the details. They're the same as the details over here. You get your omega equals this, which turns out to be 10 radians per second. There's your square root of k over m, simplifies, gives you the 10 radians per second. Okay, so now we know that this thing will naturally oscillate at 10 radians per second. Now what we're going to do is we're going to drive it with a force, or with a frequency other than 10 radians per second. Okay? Our forcing function will be like a sine or cosine of 11 radians per second, or 9 radians per second. Okay? And we're going to see what happens. And it ain't going to be pretty. Okay, then we're going to see what happens when that forcing function has a frequency that approaches the natural frequency. And I demonstrated with a mass on a spring what happens if you try to drive it at the natural frequency, which in this case would be the 10 radians per second. And then what happens if you just speed that up or slow it down a little bit, increase or decrease that frequency, it just destroys the whole thing. Okay. Then we talk about, well, we're going to do a circular model, so we better understand what's going on here, okay? And it's real important to understand this circular model because oscillatory motion is universal, okay? It's the most common motion in the universe by far. We've got to digress to what a radian means because nobody ever knows, because our education system doesn't teach people to know anything. But it's fairly straightforward, but it takes a little bit of thought, which is why our educational system doesn't teach it, because he can't do anything that requires people to think. Somebody's feelings will get hurt. I don't know. Now, I'm on my soapbox, so get off of that. But the fact that people come into engineering courses, especially second semester engineering courses, still not knowing what a radian is or how it works, is, in my opinion, sort of criminal. Smart people should be taught the things that smart people need to know. Okay, so anyhow, radian of angle, kind of there's not a rigorous definition. Radian of angle corresponds to one radius of distance along the arc of a circle, implicitly, okay? So we draw. Now I ask you to draw a radian. You did a pretty good job. That's where the radian ended up maybe around here, somewhere between here and here. And that angle actually to me looks a little less than a radian because my circle isn't perfect. So your picture was as good as mine, okay? But my picture had more explanation, so I win. Well, obviously I set the game up, so it's not really a game. Okay, you can think of a radian by thinking of an equilateral triangle. Imagine these are pieces of wire in an equilateral triangle. Now you bend this piece out a little bit so that it forms the arc of a circle of radius r. That's going to decrease the distance between these ends here, okay, between this point and this point, which will reduce this angle a little bit. But you don't have to do all that much bending, and it doesn't shorten this distance very much, okay? It shortens this angle down from 60 degrees to about 57 degrees. Did you do that, Sean? Did you calculate that?
Yeah. 7, yeah.
3? That's what I was kind of thinking. Okay, but 57.1 starts entering into my brain, and I've always been too lazy to think it through. I just didn't want to take the time, and certainly didn't want to go to a calculator to do it. Because, okay, you can do that easily. I mean, 2 pi radians, there's 2 pi radians in a circle. Why? Because pi. I could just end it there using this strange convention of the word because that you all are, I'm sure, familiar with because you kind of grew up with it. But anyhow, because I'm going to finish the sentence. Pi is a ratio of the circumference to diameter, which nobody ever knows. Again, don't go after individuals, go after our whole education system and give it a long prison sentence. Okay, it's criminal. People don't know that that's what pi is, okay? Or some equivalent. Yeah, just a number that you do this with. No, it's got a geometric meaning, but we don't teach geometry, do we? At least not at a level that'll benefit people who are trying to be engineers in their sophomore year sometimes, okay? Or they still don't know what it is. Okay, 2 pi radians then is the same as 360 degrees, okay? So radians, 108 over pi degrees, and a degree is pi over 180 radians, so there you have a conversion factor between degrees and radians. All you gotta know is this and how to use a conversion factor. Now, what does that have to do with this mass and this silly spring? Well, what it has to do with is, if you go ahead and set a polar axis here, or the x-axis here, that's okay. And if you start here, you don't have to start here, you can start anywhere on the circle. But if you start here and successively move around the circle, preferably in equal time increments, but I didn't make those equal. Like there are 4 of them between here and here, there are only 3 of them between here and here. Okay, so I just kind of slopped something down. But you see that what's going to happen is, if you project these points down to the x-axis, and these are more or less equally spaced, these are going to be the positions of your oscillator. Okay? Now, if you have a mass on a spring, you might want to think of projecting it to the y-axis. You can do that too. If it's a mass on if it's a cart on a spring that's oscillating back and forth this way, say cart on a two-spring system, you pull it back this way and it does what it does. Or a pendulum, which is easier to understand. If you release a pendulum here, it's going to swing back to here. Then because of its momentum and energy and all that, it's going to swing out to here and just keep going back and forth, right? Okay? It doesn't go real far at first because it doesn't pick up its maximum velocity till it hits here. I could explain the physics of that to you, but I'm not going to. Because not everybody's had a lot of physics or engineering, so we won't go into that. But it's intuitively obvious that that's a reasonable model for the way a pendulum swings back. It's stationary, and then it moves up to its maximum velocity. Okay, and that's the circular model. You have a reference point moving around this circle, and you project that onto any straight line through the origin, actually, but generally onto the x-axis or the y-axis, and you get a motion along that axis. And the angular position at a given time, I could do projections for all the rest of these points. You see, as we go around here, we're going to go to here, right? Then from here to here, we're coming back. And then from here to here, we go back to where we started and we do it all again. Okay, well, an arbitrary position out here, and we actually do this with a vector, but I'm not going to use the vector notation. The position of this point is going to be determined by the radius of the circle and the angle through which you've traveled from the positive x-axis. Okay? We're going to call that angle theta. But theta, well, how fast are you traveling? Well, for this thing, you're traveling 10 radians per second, right? So how do you know how many radians you're going to be at after half a second? It's going to be 5 radians, right? 10 radians per second, half a second, you're going to be 5 radians. Where's 5 radians? Well, 5 radians is around about here, okay? Actually, yeah, it's past here, it's about here, okay? To get your position here, you multiply your number of radians per second by the number of seconds. Well, in civils, the number of radians per second is omega, and the number of seconds is t. So theta equals, chalk sticking. I wanted that to be so pretty, but it just didn't happen. But theta equals omega t, right? And that should make perfect sense. So here we have this mass on a spring, this differential equation gives us this result, okay? Which tells us how fast we're moving around the reference circle. It doesn't matter how big the reference circle is, that's how fast we're moving. Just like it doesn't matter how far I pull that mass down or how far I pull the pendulum back, the reference point is going to go around the reference circle at the same rate, and it's going to take the same time no matter what. Now, again, the education system should be reprimanded for the fact that elementary students, or late elementary or early middle school students, 6th grade or so, probably haven't ever observed the fact that a pendulum swings with the same frequency with a smaller oscillation as it does with a larger one. How long does it get too large? How long does it take to do that? In 10 minutes, you can establish that convincingly in a way that students won't forget. Once they've seen it, once they've had that pendulum in their hand and measured it, they're not going to forget. So why don't we do it? Well, there are other things to be done, and you got priorities. And our system isn't real good at understanding what the priorities ought to be, which is to make me happy. Okay? Well, no. You understand, that would be very beneficial to a STEM student. And STEM's a big deal, and we're not doing it. Actually, I'm sure it's being done some places. It's not being done universally. There's certain simple things that ought to be done universally. Maybe not that one, but when you put it before an ed committee that's designing a curriculum, you get absurd results. Individuals could do better, okay? So I should just tell them what to do, and everything will be right. Maybe not. Okay, well, it's a complicated issue.
Started at 13.
Okay, so anyhow, you're a victim of this, but fix it. Okay? You want to understand all of that. Okay. So theta equals omega t. Well, the circular model tells you that if the radius of this circle is a, okay, radius circle's a, then when theta equals omega t, this is the cosine, well, a times the cosine of omega t. That's the circular definition of your trigonometric functions, and if you don't have that firmly in your mind, something very wrong with the way you were taught trig, or you just slacked. Okay? Or it's been a long time. Okay? Something's wrong if people get to this course and don't understand the circular model of trigonometric functions, and it's a handicap. Handicapped, you've got to listen to me go on about this when you shouldn't have to. Just think of how big good life would be if you didn't have to listen to me go back and tell you what you should already know, along with my side comments on my soapbox, right? Okay? Okay, well, anyhow, there we have it. There's your A cosine omega t. Okay? And if you want an A cosine of omega t plus phi, okay, well just think, okay, I start at angle phi, and then I add omega t. And I've got a cosine of omega t plus phi, because my angle will be phi plus omega t. All right? I could draw that, but kind of hope that you pick it up. And if you want a sine, of course, you could think of projecting on the vertical axis. But that's what we have. So understanding this motion. Okay, we want to understand this motion. We want to understand this motion by being able to visualize 10 radians per second around this circle, right? Now where's 10 radians? How far do I have to go to get to 10 radians? I got to go around once. That's 2 pi, a little over 6, right? I still got almost 4 to go. Okay? Well, 3 more gets me there. A little more than 3, right? So I got to go here and then a little further, probably around about here. So just to visualize it, okay, you can just think, okay, about 6 radians, okay, in a circle. So it's about 1 2/3 circles, right? But a little less because it's a little more than 6 radians in a circle. So I've got to get from here all the way around and down to here in a second. Can I do that? Let's see. 1001. I didn't get there. Okay? 1001. Made it. Okay, so it's going to run about this fast, which means that this thing's oscillating about this fast. Okay? So it's got to go from here to here, back to here, and all the way over to here, and then back to here in a second. Let's see. 1001. Got it. Okay? So it's, it's oscillating pretty fast. If you put this mass on a spring with this force constant, it's got to oscillate that quickly. Okay? Well, I think I can drive it at that frequency, but what if I try and I only get 9 radians per second? Then I've got a differential equation that tells me what's going to happen, because no way I'm gonna figure it out by trying to do it, you know, I'm not capable of keeping it that constant and then observing something that goes that fast, okay? But with the electronic means and others, I could observe it indirectly, I could find evidence of it, but, it's not practical. So instead, I'm going to solve the differential equation to see what happens. Okay? I mean, I've got stuff in here that I could use to, you know, just suspend the thing from a force sensor and run it electronically into an interface. Okay? And see what happens. Set up some circuitry to drive it at 9 cycles per second, or just, you know, one of my function generators. Okay? But I'm not going to do that. We're going to solve the differential equation. So let's say now, I don't know how much force I really want to put on this thing. So really, I kind of want to figure out what would be a reasonable force, which means I'd want to calculate the acceleration of this thing, right? Okay? So let's just say that I've got an oscillation that goes about this far, about an amplitude of 10 centimeters. So I've got a 10 centimeter radius in this circle. So that's 10 centimeters times the cosine of 10 radians per second times t. Well, if that's my position, what's my acceleration? Okay, well, velocity will be the derivative of the position function, right? The acceleration will be the second derivative. Well, it's going to be negative omega squared cosine omega t. Negative omega squared a. Okay, omega is 10 radians per second, so omega squared is 100 radians squared per second squared. Multiply that by 10 centimeters here to get the omega squared a, right? And I get 1,000, okay? What? Centimeters per second squared, okay? Which just happens to be, and I didn't make this happen, it's just that the universe is being cooperative today, which happens to be 1G. I mean, 980 centimeters per second squared. That's 1,000 centimeters per second squared. So now I know that this 0.5 kilogram mass is going to experience a maximum force of 5 newtons. Okay? I don't want to overwhelm it. I'm going to give it a maximum force of 2 newtons. Okay, maximum value 2 newtons. So I'm going to let F equal 2 newtons. I want to use the sine or the cosine, doesn't matter.
Just gives cosine.
Okay, times the cosine of ten radians per second times t. Okay? Okay. So our equation becomes y double prime plus, well, I'll write it out here, k over m. Now I'm using y, would have been using x, so I'm going to use x. Okay, we know that the square root of k over m is 10 radians per second. We actually calculated first the square of, we calculated k over m, which is going to be then 100 radians squared per second squared, right? So x double prime almost got it in there. Okay? Now those are the units. To avoid the confusion of the units, which I don't think is necessarily a good idea, but for the time being, I'm going to suppress the units and say, okay, we got x double prime equals 100, plus 100x equals 2 cosine of 2t. I said we're driving it at 9 radians per second, didn't I? Well, it's a good thing I looked at that for another reason. I really don't want that to be an integer. I want it to be a multiple of pi. So I'm going to use a multiple of pi that's close. Actually, that's not a multiple of pi. I like multiples of pi, but I'm just going to go ahead and use 9. Okay. It's going to get a little messy, but we'll live with it. Okay? So there's our equation. We know okay, instead of the e to the I omega t, e to the negative I omega t, I'm just going to use a fundamental set, cosine of t sine of 10t. Okay? So that I know my general solution is some linear combination of these. We're going to use variation of parameters because I'm sorry, I'm not going to use variation of parameters. I'm going to use undetermined coefficients. I always want to say variation of parameters because I never think undetermined coefficients, even though that's what you usually use. Okay? Now, for homework, I had you do an equation using variation of parameters and undetermined coefficients. I think, pretty sure I asked you to do one. I know I intended to. Okay? Talked about it in class. So you could do this by variation of parameters, and you'd be able to do the integral. Unlike some where the integrals are either impossible or really hard. Okay? So here's your fundamental set. We're going to use a trial solution. So we're going to use undetermined coefficients to solve the non-homogeneous equation. Y sub p equals b cosine of t plus sine of 9t. So that yp prime, and I know you can do this because you did it the other day, equals negative 9b sine of 9t plus 9c cosine of 9t. And we don't really need yp prime. All we need is yp double prime, and that's going to be negative 81b cosine of 9t minus 81c sine of 9t. Now we can plug that into the equation, and get this out of the way so I got a place to stand. And I used y again instead of x because I want to use x. Y would have made sense too, but since we're using x, I'll use x. So change that y, make it look like an x, at least semi-identifiable as an x. Okay, so we plug this into the equation, and we get negative 81b cosine of 9t minus 81a sine of 9t plus cosine of 9t, 100 cosine of 9t, plus 100 sine of 9t equals 2 cosine of 9t. Well, this tells us that A equals 0 and B equals 19, 2 over 19. And I left the B out of this. 100B cosine, 100B, 100A sine, okay? So you got 19B cosine equals 2 cosine, so B equals 2/19. So now our solution could be written C1 cosine of 10t plus C2 sine of 10t plus 2/19 cosine of 9t.